I'll try to give you I'll try to give you some general ideas relating Yang-Baxter equation, the notion of quantum integrability, and I'll talk a little bit about braces, mainly about set theoretic solutions of Yang-Baxter equation. And I will try to relate with some physical and mathematical connections, give you some connections. So first of all, let me just explain what quantum integrability is. So quantum integrability is synonymous with the idea of the exact solvability. So what exactly I mean in this context is the following. Here in this talk, I will be focusing on special class of within quantum integrability, the class of integrable quantum spin chains. These systems are interacting many-body quantum systems whose eigenvalues and eigenstates can be computed exactly. And this is precisely what I mean with the notion of exact solvability. There are systems that can be computed exactly in this sense of solving the problem of eigenvalue and eigenstate, which of course is extremely complicated when you're dealing with n-body systems. So these systems have, of course, a lot of physical interests. Integrable quantum spin chains lately have been used to describe the so-called ADS-CFT correspondence. They play an important role in the context of string theory and gauge theory duality, also in the study of non-equilibrium systems, in understanding physical notions that like quantum entanglement and so on. But also they have a lot of mathematical interest. We already heard a lot about Yang-Baxter equation connected to quantum groups. But I want to say I'm going to take a completely different point of view, and I will examine the Yang-Baxter equation and the quantum integrability and the role they played in understanding the quantum algebras associated with quasi-Hopf algebras and quasi-triangular Hopf algebras, their connections with braid group and Hecke algebras. There are also connections with cluster algebras, combinatorics, representation theory, and so on. I will try to talk about the three or first of them, the connection with quantum algebras, Hopf algebras, and braid groups. I have been asked to be to go very slowly and be very elementary. So most of people, perhaps they don't have this background. So I'll try to go slowly. Please interrupt me if you have any questions. So a formal definition of quantum integrability is the existence of a family of mutually commuting algebraic quantities. Of course, this family is guaranteed for any system that is governed, is ruled by the Yang-Baxter equation. I've been written this equation here. I will explain later on what these indices and these constants lambda n and lambda 2 mean. So from a physical point of view, this equation describes the factorization of multi-particle interactions. So if you have three particles interacting, the Yang-Baxter equation shows you the way that the interaction is factorized in two-particle interactions. Algebraically, as I said, gave the first boost of developing the quantum algebras and the connection with braid groups and Hecke algebras. I will try to give a first overview on those. So the moral of the story is that Yang-Baxter equation is essentially synonymous to quantum integrability and to the notion of quantum algebras. Every time you hear the word Yang-Baxter equation, it's guaranteed you're going to deal with some quantum integrable system and with some underlying quantum algebra. So I'm sure in this audience, you've all seen this equation, which graphically represents the Yang-Baxter equation, and the indices 1, 2, 3, from the physical point of view, are attributed to particle 1, 2, and 3. And this factorization, this way or that way, expresses the three-particle interaction. Every time you see this node here, you have an R matrix. So this is R1, 3, this is R2, 3, and this is R1, 2, and so on. So this is a graphical representation of the Yang-Baxter equation. So before I go ahead and give you the basic ideas associated with quantum integrability and Yang-Baxter equation, let me just briefly review some history about this equation. The first time Yang-Baxter equation appeared were back in the 60s in the work of Yang, who studied an n-particle interaction in the presence of a delta potential, and later on by Baxter in early 70s, 72 and 73, who studied and solved the so-called XYZ model, which is the completely anisotropic Heisenberg model that describes, basically explains the magnetism in nature. Yang-Baxter equation and the R matrix, of course, are the quantum analogs of the classical Yang-Baxter equation and the classical R matrix. People that have seen that, they know the notion of Sklianin bracket. People like Sklianin and Semenov-Tianshansky have studied a lot at the level of classical integrable systems. And then later on, this equation played the fundamental role in the so-called quantum inverse scattering formulation. I will try to speak a bit about this and how the quantum algebras appeared in this quantum inverse scattering formulation, and then how Drimfeld and Jimbo, motivated by these findings, formalized the notion of quantum algebras, and Drimfeld realized these algebras are quasi-triangular Hopf algebras. So whatever you try to do, either your question is mathematical or physical, the first step is to try to find solutions of the Yang-Baxter equation. There are various ways to do. For instance, we can use the braid group and some quotients like the Hecke algebras to find a representation of these algebras, and then using these representations via a process which is called Baxterization, first introduced by Jimbo, find solutions of the Yang-Baxter equation. Or if you have already a quantum group symmetry at hand, you can use certain intertwining relations to identify the R matrix, in particular the so-called universal R matrix. Here I'm going to consider the first approach. I'm going to use the similarity between the Yang-Baxter equation in a certain form, in the braid form, and the braid group, and then find representations to find solutions. Then Drimfeld introduced, I'm continuing with a historical path, somewhere in the 90s introduced the notion of set-theoretic Yang-Baxter equation, set-theoretic solutions of the Yang-Baxter equation, and Hinderinen was the first to classify such solutions. Later on, Ettingov, Sedler, and Soloviev found set-theoretical solutions and associated quantum groups for parameter-free R matrices. There are very interesting connections with the so-called geometric crystals and cellular automatons. And also, these set-theoretical solutions have been extensively used and primarily used in classical integrable systems as discrete time maps, the so-called Yang-Baxter maps. And there's a whole bunch of people working on that. But recently, we tried to extend the study on the quantum integrable systems, quantum spin chain systems. Lately, let me just say what is more relevant to this audience is that set-theoretic involutive solutions of Yang-Baxter equations coming from braces. There are a lot of people in this audience that are experts in finding such solutions from braces or skew braces, which I'll try to say very briefly what a brace is. And so all these ideas together ended up to what we're going to talk today and the next days of this workshop. So what is the aim of this talk? I will try to make a big review about the notion of the R matrix and the Yang-Baxter equation and how it's related to quantum integrability and also to the idea of quasi-triangular Hopf algebras. And I will later on introduce the set-theoretic solution and establish this solution connections between the solutions coming from braces and quantum integrable systems. In particular, we'll derive some new quantum algebras coming from braces. Yangian is a special case within this larger class. And then I'll move on constructing a new class of physical quantum integrable systems with this R matrices coming from braces. And employing these solutions, I will find some symmetries of this, exact symmetries of these physical systems. I will explain what I mean by exact symmetries. Finally, if I have some time, and I hope I will have, I will recall the notion of the Drinfeld twist and how one can express these set theoretic solutions as Drinfeld twists. Okay, I already told you what I'm going to say about. So let's start from the very basic. What is an R matrix? Here I'm going to consider R matrices which are represented objects and act on R n square by m square matrices and satisfy the Yang-Baxter equation, which acts on the tensor product of 3 n-dimensional vector spaces. Let me explain the indices 1 and 2. So index 1 and 2 means that these are matrix, acts non-trivially on the first two copies of the tensor product, and the third one is trivial. And I can write it in general in this form. And this is in general some amplitude, some C number, which is associated for statistical system with what is known as a Boltzmann weight. And this object Eij are n by n matrices with 1 at the position ij and 0 elsewhere are in fact the representation, the fundamental representation of GLN. R13 similarly means that this matrix acts non-trivial in the first and the third, and so on. So this is the index notation I'm going to adopt here, and lambda 1 and lambda 2 are some complex constants, which are called for historical reasons spectral parameters. All right, so allow me to introduce now a new object that Jimbo was the first to introduce, is the so-called R-check, which is the permutation operator, which basically swaps the two spaces times R. And this R-check satisfies the Yang-Baxter equation in the so-called braid form. So you can write it in this form. And notice here, this equation is a bit different than this. So here you have R12, R23, R12, R23, R12, R23. And this is in fact a braid relation if you look carefully. So now, as I promised, I'm going to use the similarity of this equation with the braid group, with the defining relations of the braid group. And I will try to use a representation of this group to find solutions of the Yang-Baxter equation. So let me remind you what is the A-type Martin braid group is defined by generators Gi from 1 up to n-1, and the following exchange relations: Gi plus 1 Gi is equal to Gi plus 1 Gi plus 1. Okay, so this one is a special case just for I equals 1. And of course, these generators commute if this indices L minus M is bigger than 1, the absolute value. Graphically, this is the way a braid is represented, is a braid indeed, that lives locally at the positions I and I plus 1 in this sequence of indices from 1 up to n. All right. Of course, the braid group is too big to be physical. And remember, my main motivation here is to try to build something physical. If you want to build something physical, you need some extra constraints so that unitarity, for instance, is ensured, crossing unitarity is ensured, and so on. So in order to do that, I have to play with some quotients of the braid group. And the first quotient is the A-type Hecke algebra, which defined again by the n-1 generators Gi that satisfy the braid relation that commute if L minus n is bigger than 1. But an extra constraint is imposed, the Hecke constraint, which of course is going to guarantee that my R matrix is going to be unitary, which is great news if I want to build a physical system. Okay, so I will be focusing here in the special case where Q is 1. So this is nothing but the symmetric group in a sense. And I'm going to look for the presentation of this type, Hn, on some tensor product of n-dimensional, Kerrli n-dimensional spaces. And if I consider such a representation, H element Gi is going to map in this object R check I plus 1, which I can write it in this form. So this R check lives in these spaces, in this position I and I plus 1 of the tensor product. And of course, the simplest solution of the braid relation, which satisfies all this relation, namely P satisfies the braid relation, and also P squared is 1. So it satisfies this relation in the case that Q is 1. Indeed, if Q is 1, this relation is translated to G square is equal to 1. So this is the simplest relation of this symmetric group. And indeed, for any representation of, as I said before, of this Higgs algebra for Q equals 1, R satisfies the braid relation written in this form as a tensor product, or R squared is 1, is involutive in the sense. So given that R check satisfies the braid relation and involution, you can easily show that by the process that is called Baxterization, you can introduce an extra parameter lambda, and you can show that if R check satisfies these two relations, then this solution, R check lambda is on lambda equals lambda R check plus 1, satisfies the Yang-Baxter equation in the braid form, and hence this relation here, R lambda is lambda times R. I have it with blue, I'll explain why, plus P, also is a solution of the Yang-Baxter equation. Okay, so this gives me a solution of the Yang-Baxter equation that also guarantees integrability, namely R of lambda times R of minus lambda gives me something which is proportional to 1. R minus lambda gives me something that is proportional to 1. Okay, notice here that if this R, this blue R, is the identity matrix, then I recover the so-called Yangian, which is well known at quantum algebra. But here I'm going to consider solutions that are of this form, where R satisfies these two relations, the braid relation, and it's also involutive. So such solutions, as I'm going to explain later on, are associated to set theoretic solutions that are coming from braces. And if I relax this condition here, so involution is not guaranteed, then one can deal with solutions coming from the so-called skew braces, but other speakers will give details on those. Okay, then from now on, I'm going to consider the solutions. But let me, before I play with such general solution, introduce some ideas from quantum integrability, and let me start with the so-called FRT construction. What this construction tells you, if you have a solution of the Yang-Baxter equation, finite solution of the Yang-Baxter equation, then you can define a quantum algebra via the so-called FRT construction, shorthand for the names Fadeev, Reshetikhin, and Takhtajan. So this quantum algebra is defined by this fundamental relation. R check is the way I defined it before, P times R, and L1 and L2 are basically n by n matrices, which with entries that are elements of this algebra L. Okay, so so this is the defining relation of this algebra A. So if I give you, I repeat, a finite R matrix, you can write this relation here, and you can find, identify the quantum algebra A. So again, I will remind you this index notation. R check 1, 2 means simply that, R times the identity. L1 means this. So this is the n by n matrix and elements. Tensor product LZW, where L and ZW are the elements of the algebra A. Similarly, L2 you can express it in this way. So if you have a solution R, specific solution R, and you plug in all this expression in here, you are able to find what are the exchange relations between LXJ and find the form of the quantum algebra. Okay, so let me give you an example. The simplest example in this class is the Yangian. And a finite solution I already gave you is this one. Our check is lambda p plus the identity. P, I remind you again, is the permutation operator, which has this general n by n form, n squared by n squared form. So if I have this Yangian solution and I express L as a formal solution, as a formal expansion in powers 1 over lambda, where Ln is given in this form. If I plug everything in my RTT relation, in this one, then this is the fundamental set of relations that I find. Remember, this upper indices n and m just show you the order of the expansion. And these are the fundamental relations of the GLN Yangian, coming from FRT. Usually people use some other notation. In fact, people consider the logarithm of L and find a new set, an alternative set of generators, usually called Q. It doesn't matter, it's equivalent description. It turns out that this is a quasi-triangular Hopf algebra. I'm not saying exactly now what this quasi-triangular Hopf algebra is. I will explain later on, very shortly. But what is important to note is that these relations here are true for this algebra. So you have a coproduct that has this form, you have an antipode that gives you the inverse L, and you have a co-unit which gives you the identity. The coproduct is guaranteed by RLL, but these two equations, if you have some other elements, you cannot show yet. All right. So if you have this RL relation and you have a finite R matrix, you have a way to find the exchange relations of the generators of the underlying quantum algebra. So an interesting corollary is in the case of the Yangian, the finite GLN is realized by the elements L1 of the first order of the expansion. Indeed, if you focus in the case where this n is 0 and m is equal to 1, you get the defining relations of GLN. This is an interesting observation. Later on, we'll need that when we're dealing with physical systems and how this relation is modified in the case we're dealing with set theoretic solutions. Okay, and now we come to some definitions. I'm sure most of you have seen this definition, know these definitions, but because I was asked to be simple for students, I will, I'm sorry for people who already know that. So what is a bialgebra? Is a vector space over some field K with some linear maps is the multiplication. You have two elements of H that are mapped, H tensor H mapped on H, the usual multiplication AB, and this is associative for any ABC that belong to H. You have the so-called unit that takes you, unit element that takes you from K to H. K is the field, such that eta of 1 gives you the unit element of H. You have the coproduct, which is a map from H to H tensor H, in general written in this form, where AJ and BJ are elements of H. And this is co-associative in the sense that this is true. Delta acting from the left and from the right on the coproduct of each element gives you the same quantity. And the co-unit from H to K such that these are true. Epsilon from the left and the right bit of your acting on the right and left bits of the co-product gives you the same element. Delta and epsilon are algebra homomorphisms, and H tensor 8 has the structure of a tensor algebra. Namely, this is true. So in other words, the algebra H, A, M, and eta is an associative algebra, and H, delta, and epsilon is an associative coalgebra. Okay. Let's go a bit further. What is a Hopf algebra? Is a bialgebra equipped with a bijective map, which is an antihomomorphism, and they called the antipode, such that this is true. Again, action of S on the tensor product on the left and right bits, and the multiplication of those gives you some constant times the unit element of H. And finally, what we're most interested here is the definition of the quasi-triangular Hopf algebra, which is again a Hopf algebra. It has all the previous axioms satisfied over some field K. Then A is a quasi-triangular Hopf algebra if there exists an element R on A tensor A, invertible element A, such that these axioms are true. You have this R delta A is delta opposite A times R for every element of the algebra. Delta opposite is just pi tensor delta, where pi is the flip map such that it swaps again the two positions of the tensor product. And also you have this rule of co-multiplication, identity tensor delta on R. It has this form, R13, R12, and delta times identity, it has this form. In fact, if you put these things together, it turns out that the R matrix has to satisfy the Yang-Baxter equation. It's easy to show that these things, two things together, lead to the R matrix to satisfy the Yang-Baxter equation. Also, you can show using the axioms that the antipode acting on R minus 1 gives you R, and S times identity R gives you the inverse of R minus 1. And also the co-unit satisfies this relation here. And as I said at the beginning, due to the axioms of the quasi-triangular Hopf algebra, the R matrix satisfies the Yang-Baxter equation. If in addition this relation holds, R opposite is equal to unit of the tensor product, then the algebra is called a triangular Hopf algebra. Basically, we're going to deal with triangular Hopf algebras here. Okay, so just a note here. I explained a bit in detail the so-called FRT construction. So this construction is somehow dual to the derivation of our matrix via the axiomatic approach, via the axioms of the quasi-triangular Hopf algebra. In particular, in the FRT construction, the R matrix is the input and the quantum algebra is the output, whereas in the axiomatic approach, the algebra is the input and the R matrix, in particular, the so-called universal R matrix is the output. And although here we can start with a finite R matrix, you can build up in certain ways the universal R matrix of the quantum group and also build the quantum algebra. Okay, so let me now so far discuss some general algebraic ideas associated to quantum algebras and Hopf algebras and Yang-Baxter equation, but let me now come to the construction of physical systems using tensor representations of the underlying quantum algebra. So we introduce an object, which is a tensor matrix, which is indeed a tensor representation of a quantum group, in a sense that the tensor matrix is a tensor product of n R matrices. So T acts on this tensor product and of orthogonal tensor product of n+1 dimensional n-dimensional spaces. Historically, this index 0 corresponds to the so-called auxiliary space. So this notation and the name auxiliary is for historical reasons associated to classical integrability and the monodromy problem there, and the auxiliary linear problem there. Whereas the indices 1 up to n are called phantom. Here I just suppressed the indices for brevity. So we have this object, and now we take the trace over the auxiliary space, and we define the so-called transfer matrix as an object that takes its name from statistical physics, from statistical mechanics, and this object lives is an element, an n to the n matrix, Kerley n to the n matrix. Due to the fact that R is the solution of the Yang-Baxter equation, you can show that T satisfies the fundamental relation RLL I wrote at the beginning when I discussed the efforting construction. And also, due to the fact that T satisfies the RLL relation, you can relatively easily show that for different parameters lambda and mu here, these objects commute. In fact, this transfer matrix is the generating function of the integrals of motion, of the family of integrals of motion of quantities that are in involution commute with each other. Indeed, you can write T as a formal series expansion, and then you can show, of course, from this relation that each order commutes with the other one. This, of course, is the definition of quantum integrability in line with the definition of a la Liouville of classical integrability. But of course, then you need to be careful about showing that each one of these integrals of motions decay, the conserved quantities, are independent among them. So another interesting observation here is that if you have, this is something we proved with Agatha, that if you have such an object, such solution of the Yang-Baxter equation, where R check is a solution of the braid relation, then you can write the Hamiltonian, and in fact, all the elements of all the conserved quantities, or the higher Hamiltonians, if you wish, expressed in terms of Hecke algebra elements. In fact, the Hamiltonian can be expressed in this form. So these are all the elements of the Hecke algebra, but you have this annoying periodic term, and I will explain why this term is annoying later on. And you can write up higher Hamiltonians this way. So this is the first Hamiltonian, and this is the next one, and so on. The idea is that you can write all the n conserved Hamiltonians in terms of the Hecke algebra elements, plus some annoying periodic terms. Okay, so for instance, in the case of the Yangian, where R check is the permutation operator, this is the kind of local Hamiltonian that you get. I insist very much with the term of Hamiltonian because in statistical systems, as you probably know, this Hamiltonian gives you the energy spectrum of the system. So you gain a lot of information about the physical behavior of it. In the special case of SL2, you can write the Hamiltonian in terms of 2 by 2 Pauli matrices that are the fundamental representation of SL2. And you can see here sigma x, sigma y, and sigma z are the Pauli matrices, and you have a spin-spin first neighbor interaction. This is the XXX, or the totally isotropic Hamiltonian. If you have a constant here different to 1, then you're dealing with the anisotropic XXZ model. And if you have an other constant different to this one, you have the XYZ Hamiltonian, and so on. So we have been able, using this kind of algebraic construction, to build up physical systems like the ones here. So let me just very briefly tell you that in the case of the Yangian, all this family of this tower of conserved quantities of Hamiltonians are, this is the tower of conserved quantities, this M runs from 1 to n, is GLN symmetric, okay? Which means that these objects here commute with the tensor products delta n EAJ. EAJ, remember, are fundamental representations of GLN, and the n coproduct has the general form. So the 2 coproduct is the familiar 1 times CIG plus CIG times 1. So indeed, you can show that these elements, the first order in the expansion of the monodromy matrix. The elements of the matrix T in the first order of expansion are in fact the n co-products of the AJ elements, which are the generators, of course, of GLN in the fundamental representation. So indeed, these TMs commute with this delta n, so we can say that these Hamiltonians are GLN symmetric. This is precisely what I mean with the notion of symmetry. You will tell me, why is this interesting? This is particularly interesting because the ultimate goal when you have such such quantum systems, statistical systems, is to study the eigenstate and eigenvalue problem, as I said at the beginning, the spectrum of these Hamiltonians. And you can study the spectrum of this, all these commuting Hamiltonians at the same time via this various methods, for instance, algebraic bit ansatz. But knowing the exact symmetry of the systems gives you a lot of information about the behavior of the spectrum. The more symmetry you have, for instance, they have the more multiplicities you have in the spectrum. So it's one of the first things you need to study when you have such a system. So far I've been very generic, and I just used the Yangian as the simplest example to give you an idea. But let me now talk about more general set of solutions of the Yang-Baxter equation, the so-called set theoretic solutions. So let me deal with, I will be dealing with finite set here, X, with elements x1 up to xn, and let R check be a map for X cross X to X cross X, the Cartesian product. And let me denote R check X of Y being sigma xy tau yx. So this R check maps this pair xy to this pair, to this new pair. So if this solution R check X R check is a non-degenerate, it means that sigma x and tau y are bijective functions. And also if X R check is involutive, it means that R square R times R check xy gives you again the same thing. So R square is somehow the identity. So here I'm going to suppose that my solution is an involutive, non-degenerate solution of the Braid equation. So it satisfies this Braid equation in the Cartesian form, in the set theoretic form. But of course, I can always linearize and write this equation in the tensorial form, in matrix notation. So let V be the space of dimension equal to the cardinality of X. Then R check is the n squared by n squared matrix, written in this form. Again, this is kind of the amplitude or the Boltzmann weight. And for set theoretic solution, this amplitude R check is obviously of this form. Okay. So we're talking about a product of delta distributions. So then if you substitute this combination here, I immediately can tell that R check has this form, this simple form. Again, the special case of the Yangian, sigma and tau are just the identities. So R check is this one. And in this case of the Yangian, R check is the permutation operator. So indeed, it's a special case of the general solution. So here we come, how we connect these set theoretic solutions with braces. I will just say the definition and the general theorem by Ram, because as I said, many people today and tomorrow will give more details about braces and skew braces. So what is a left brace? Is an abelian group together with a multiplication such that this operation, circle operation, defined this way, makes B into a group, and also associativity is guaranteed here. And if this is true, and given the definition of circle, then you can show this relation is true. Okay. So this is definition of a braid, and here comes the fundamental theorem by Ram that says if you have a brace B, and X and Y are elements of this B, we can define a map this way. the Yang-Baxter map, such that sigma x and y is this, and tau y of x is this one, where this -1, the inverse, is with respect to the circle operator. Then B of R, sorry, check here, I meant, is a non-degenerate involutive solution of the set-theoretic equation. And conversely, for every non-degenerate involutive solution of the set-theoretic Yang-Baxter equation, there is a brace, which is a restriction of the Yang-Baxter map. So it's you can see one or another. So this is all I'm going to say about braces and the Yang-Baxter equation. And as I said, I'm going to focus on finite involutive non-degenerate solutions of the Yang-Baxter equation. So these solutions I'm dealing with, they always come from braces. Sometimes I'm going to call them brace solutions. So I'm going to focus on the solution, which is a representation of the 8A-type Higgs algebra. And this is the factorized solution. So if I focus in these solutions, I can prove this relation, which is called the unitarity, and is very important in our context. I can show cross-unitarity, expressed in this way. T1 and T2 denote transposition in this position 1 and 2 respectively, and the total transposition of 1, 2 gives you R2, 1, swaps the position. So it's R2, 1 is defined like that, where P is the permutation operator. So I'm happy because all the physical quantities are satisfied. And now I go back to my RTT relation and try to construct my new quantum algebra. So I plug in the R matrix I wrote before, this R matrix here, and the specific set theoretic solution. I substitute L1, L2, and I do this expansion in powers of 1 over lambda, and this is the non-trivial quantum algebra that I find for all orders. These are the generators of all orders. This is a general and a fine algebra, okay? And the question is, the fundamental question I'm going to ask, is this indeed a quasi-triangular Hopf algebra? The question is no. The easy question would be, okay, I have a Yang-Baxter equation underlying. I would expect that the quantum algebra that one can obtain from the RTT relation, the obvious thing is to be a quasi-triangular Hopf algebra. Well, it's not. I'm afraid that I don't have the time to explain why, but very soon there will be a preprint on the archive about that. I will try to explain very briefly, focusing on a simple solution, a theoretic solution, the so-called Ljubasenko solution. So here, let T and sigma in maps from X to X, and by isomorphism such that sigma Tx is equal to T sigma X is X, so one is the inverse of another. And let me introduce this matrix V, and by matrix V of this form, Ex of Tx and V minus 1 having this form. Then any solution of this type, this is the so-called Ljubasenko solution, can be obtained immediately from the operator, permutation operator, in a very simple way, in this way. So V acting in the first space, V tensor 1 P tensor V minus 1, and similarly, this is true. So our check, if you plug in the form of V and the form of V operator, you immediately end up to this expression here. So in fact, this V tensor 1, it turns out to be a so-called simple Dirichlet twist. I didn't say anything about Dirichlet twist, and I'm afraid I don't have much time. So for this simple case, we have a Dirichlet twist, so we can make a connection between the Yangian and the quantum algebra associated to Ljubasenko solution. And in fact, we have been able, in a recent paper, I have been able to identify the general Dirichlet twist for any set theoretic solution. So this is a very important result, to be able to identify a Dirichlet twist for such solution, because you have equivalence of underlying quantum algebras, but not necessarily at the level of Hopf algebras. And in fact, it turns out that although you start with a Yangian, which is obviously quasi-triangular Hopf algebra, the algebra that you obtain after twisting is not a quasi-triangular algebra anymore. And there is a reason for that. Unfortunately, I don't have the time to explain. I have only time to give you some twisted coproducts. So if our check is a Ljubačansk solution, which I wrote here, this one, the simple one, and these are some examples about sigma and y, and that belong in this set of numbers from 1 up to n. Then this special solution is GLN symmetric. So our check commutes with this delta I. I takes two values, 1 or 2. So you have two distinct twisted coproducts. The one is this, E sigma x sigma y tensor 1 plus 1 EXY. So you have some twisting here, whereas in the other, the alternative coproduct, you have a twisting here. It's easy to show that this twisting still tells you that delta 1 and delta 2 satisfy the GLN relations, defining relations. And you can easily show that this delta 1 and delta 2 commute with the Ljubačansk solution. The proof is very easy. The permutation operator P commutes with the GLN coproduct, delta EXY. Then all you need to do is to multiply this relation here with this object, V tensor 1 from the left and V minus 1 tensor 1 from the right. And this way you obtain delta 1. And if you multiply with this object from the left and the right, then delta 2 is the alternative coproduct. The question now is this coproduct satisfies co-associativity? The quick answer is no. So since you don't have co-associativity, you don't have one of the axioms of the Hopf algebras, so you have to look a bit further and a bit deeper. I'm not going to raise this issue here. I'm just give you some hints that we're not dealing with Hopf algebras anymore. So we have to go a bit further. All right. This was the algebraic part. I just gave you a simple example because I don't want to get into technicalities given the limited time. I remind you again that you can now build the physical system. I repeat, just to remind you how we get such systems by this tensor product. The Hamiltonian in the universal form is this one, but now our check has a particular form. So the set theoretic, in general, the set theoretic Hamiltonian, first neighbor interaction, as you can see here, has this form. It's highly non-trivial. And I'll give you an example to show you how non-trivial this expression is, even in the case of the simple Ljubačansk solution, which you can obtain from the Yangian via this simple twist. So unlike the Yangian, this periodic Hamiltonian is not GLN anymore. Well, this comes as a surprise because I would expect, at least for the Ljubačansk solution, to get some symmetry. But the truth is that the symmetry is spoiled due to the periodicity, due to the periodic term. If I didn't have this periodic term, namely if I considered an open topology for my chain and not the closed one, a ring, then GLN symmetry would be restored. But this information tells me that I have some information about the spectrum, which is highly non-trivial, okay? So it tells me that in the case of the Yangian, I have high symmetry, namely lots of multiplicities in my spectrum, but this is not true in the case of the set theoretic solutions. So I already have some information at hand. A second bit of information, very important again for the spectrum, is to identify the Drinfeld twist for the general solution. And this has been done in general for the Ljubačansk solution and the general solution. So I have that also at hand. So I can combine these pieces of information and start building the spectrum, the eigenvalues and eigenstates of such highly non-trivial Hamiltonians, which are kind of combinatoric Hamiltonians because they give you all possible combination between the indices of the set. And hence you get various different physical systems. What I can say about this case of Hamiltonians is unlikely the case of the Yangian, where you have a full GLN symmetry. Here, if you consider a special set of set theoretic solutions that satisfy this condition, namely you have a subset from fields from elements x1 to xk that belong to x for some specific k, and you assume that this holds true, that basically for this subset R basically is the permutation operator for every y of x, then you can show that the transfer matrix is GLK symmetric. Again, the proof is relatively easy. You go back and you prove that the R matrix it's GLN symmetric, namely GLK symmetric, namely commutes with all these elements. And if you prove that, you can immediately then prove that the whole monodromy matrix satisfies with this n+1 coproducts. And then if you have this information, you can show, it takes some effort, for particular indices of elements of the monodromy matrix, you can have various exchange relations. But at the end of the day, it's the transfer matrix, namely the trace of these objects, the sum of these objects you want to deal with. And if you take the trace, indeed, you can show that the transfer matrix is GLN symmetric, namely it commutes with these n coproducts. So at least you have some symmetry for this special class of set theoretic solutions, which can give you again important information about the kind of multiplicities you will find in your spectrum. Well, let me just give you a very brief idea about Drinfeld twists. I think I have a couple of minutes. So if you have a quasi-triangular Hopf algebra and an element, an invertible element F, which is belongs to A tensor A, and you also assume that this condition holds, then the twist of A generated by this element F defines a new quasi-triangular Hopf algebra. This was shown by Drinfeld. Notice here, this is very important, this condition holds true. And then we can define a new R matrix via this relation here, okay? Where F opposite is pi, some composition F. And pi again is the flip operator. And also, if you define U as this object, then this is invertible, it's easy to see. And this is U minus 1. And the twisted maps then have this form. Of course, this is easy to show given the first of the axioms of the quasi-triangular algebra and the definition of this. And also you get a twisted antipode. I already show in the case of the special case of Ljubojensko solution that the twist is very simple, is 1 over V, for instance, and is an admissible twist, namely it satisfies this fundamental co-cycle relation, this one. Namely, not exactly this one, is this one times something, which tells me that there is a kind of co-associator. In any case, in the case of the quasi-bialgebra, from quasi-bialgebra to quasi-bialgebra, this is the relation that one needs to satisfy. So for the set theoretic solutions, we have been able to identify F in general. I have been able to identify some co-cycle condition, which is almost this one, but not quite. And I have been also able to find the general N twist, which has this form. The 2 twist has this form, namely, if you take F times F minus 1, you're going to find R check. It's very easy to check even as we speak. And then using an appropriate co-cycle condition, which I don't have the time to give you the technicalities, but trust me, there is such a condition. You are able to identify the N+1 twist. And then in the case, for instance, of Ljubojensko solution, this is the N twist. It has this form, 1 tensor V, tensor Y squared, and so on, okay? And once you have such a general twist, here it comes the most important idea and how you can exploit it to find information about the spectrum. You can show that the twisted monodromy matrix comes almost as a gauge transformation, not Y, because you see here a different order in the indices. Nevertheless, you can write in specific form the monodromy matrix. I'm not going to show this here. It's in the original paper of Drinfeld and in many other places on quantum groups. And now what this basic proposition or theorem tells me that if you have a monodromy matrix that you know the spectrum of, then you can relate it to the twisted monodromy matrix, and you can find information about correlation functions. And in fact, this is how it was the first important computation of physical quantities like correlation functions in statistical systems using these Drinfeld twins, which related the so-called Godin models, diagonal Godin models with easy to compute spectrum and the XXZ spin chains. So we'll stop somewhere here. I will repeat that the findings of Drinfeld twins and symmetries are extremely important for our ultimate, extremely complicated ultimate goal, which is to find the spectrum of such new systems. I already mentioned something in Drinfeld twist. In most of the cases in the literature, you see this condition to be satisfied. In our case, this condition is not satisfied. So you get something new as a result. So far, I only restricted my attention in the case of periodic systems with these annoying periodic terms and so on. But with Agatha, we also studied systems with open boundary conditions where the whole algebraic structure and the symmetry structure is much more interesting and easier to deal with. And in fact, there is a hope that we will be able to find, to solve the eigenstate problem for such open systems in a more straightforward way than the periodic ones. Well, I think I will stop here. Thank you very much